Welcome back, everybody. So let's see. Right now, we're finishing our first full week together, and I hope by now we've sort of started to smooth out any bumps that appeared along the way. And we've built a lot of tools in our toolbox already. So we've learned geometric optics, though we're not going to talk about that today, but we've also learned kinematics, dynamics, conservation of momentum. We know everything there is to know about mechanics, right? No problem. Well, maybe not everything, because we have today's lecture, which is energy. Um, and energy is a term that we use in everyday speech as well as a term we use in physics, and we use them a little differently. So we're going to start with the definition, um, but that definition is going to change over the course of this video. So what I actually want to do is give you a few moments. You're going to pause the video and write down a definition for you for energy and write down a few words that you associate with energy. It could be types of energy, anything really that comes to mind. And we're going to refer back to these a few times. Okay? So go ahead, pause the video and do that, and then come on back. Welcome back. So you have your definition, you have your words. We're going to start with, as we start with all these topics, at a practical definition of energy. What do we care? Like I said, we have all these tools. We're mechanics, rulers here. So what can we do? Or why would we need this new thing called energy? Well, my first definition of energy is going to be energy is the thing we use when kinematics no longer works. So it's the thing that we rely on when we need it. And so let's find out maybe a situation where we need it. We're going to start with a situation that seems pretty simple, but if we try and attack it using the tools in our toolbox, we're going to run into problems pretty quick. So what we've got here is a ball going down a ramp, and the goal is to put the ball at a height such that it will go around the loop-de-loop and stay in contact with the loop the entire time. And ideally, what we'd like is the minimum height that we can do this, because we know that if we, for instance, go from way too high, it'll go right around. But if we go a little bit too low, it's not going to make it. So that's the goal. Okay, let's try and do this. So we're going to start with our ramp. Straight line, sine theta t, or if we use the hidden formula, say, well, now we're going around this circle, right? And so that's a bit of a doozy. A parallel times t, but this is not constant. So we're actually going to have to integrate. So that's it. That's the issue. So we're going to say v. So we're going to have to figure out how time depends on our angle. So what the heck was that? This is as simple as it gets, right? We just have a ball rolling down a ramp. And we can't solve that using kinematics? This is ridiculous. Well, there's a few things that we missed in our kinematics description that we can find in our video that might help us out. And so that's what we're going to try and capture using this new thing that we're calling energy. So why don't we go back and look at a couple of features of this system that weren't respected when we or weren't accounted for when we just used kinematics and the rest of our toolbox here. Here I've now brought in a closer angle on our trajectory, and we can look for a few features. The first is that kinematics ultimately failed because it only deals with constant accelerations. But it's worth noting that the only force that acts to accelerate our ball at any time is gravity. It acts at different angles, but it's only gravity. And the other thing I want to point out is that the height that the ball reaches is very similar to the height that the ball starts at. All right, so we found a few things that weren't being accounted for. So we know that that's probably the key to us figuring out what kinematics missed. And so now we want to combine this with everything else we know about energy to try and make a new definition. something that we can really use to fulfill our first one, to the thing we use when kinematics doesn't work anymore. So now we're going to go back to those lists of words that you associate with energy. And I made my own list because I didn't get the chance to talk to you before I filmed this video. And here are some of the things that showed up on my list. And basically, there's two regimes of things. And I'm going to separate them off into types of energy and dictionary definitions, word associations that we're going to use here. So here in types of energy, you get what kinds of things have energy associated with them. And so some are like gravity, where you have, the energy due to falling from gravity. Motion, electrical energy, nuclear energy, so on. So these are all great, important things, but ultimately they're going to just describe where our energy is coming from, which is not the source of this video, which is just about energy as a whole. So I'm just going to push those off to the side for now. Over here, we have our words that we associate with energy, and this is where we're going to look for a little bit of intuition to help us build out what we think of as energy. And so I'm going to take these first two things, which some of you may have thought are a type of energy, kinetic energy and potential energy. And we're going to try and define those. So kinetic energy, pull that over here. Kinetic energy is the energy associated with motion, the energy associated with kinesis. So simply the energy of something moving. Potential energy is sort of everything else. It's the energy that could be used to move but isn't currently. So that's sort of everything there. That covers everything because you're either moving or you're not. So you either have kinetic energy or potential energy, and you're good to go. These definitions will come up a little bit more later, but it's good to have them in our back pocket. So for right now, I want to focus on these three remaining words: work, conservation, and symmetry. And we're going to start with the top because it's going to well introduce us to our second definition of energy. And this second definition might even be one that some of you wrote down because it's the most common one that's written in physics textbooks. So if you cribbed your answer, this is probably what you wrote. All right, speaking of cribbing our answer, I'm going to read these two definitions right off of Wikipedia. So our definition for energy is, in physics, energy is the quantitative property that must be transferred to a body or physical system to perform work on the body or to heat it. Okay, so this definition is the worst kind of definition because it doesn't tell you anything. It's energy is this thing that has to be transferred to perform work on it. Well, what does work mean? Hence this definition over here. Well, also off of Wikipedia, work in physics is the energy transferred to or from an object via the application of force along a displacement. Well, this isn't a whole lot better, is it? Work is the energy transferred to or from an object, and energy is the thing that does work. So we're really just going in circles here, right? Well, not quite, because we get a little extra piece out, which is in our definition of work is the force along a displacement. So here's yet another clue that force along a displacement is the method that we use to transfer energy. All right, so I want to make a little bit more sense out of this force and displacement thing. So I'm going to pull in our sources of energy again, and I want to look at each of them and parse. We know these things create energy. How do they do it? Well, if we start at the top, we have gravitational potential energy. And the way that works is there's this force due to gravity that acts in a displacement. When you move down, you gain some energy from gravity. If you move up, it takes energy to do that. So, okay, so that's how this sort of system works. If I go down the list, if we go to electrical energy, it's the same story, is that we have a force between charges, which we'll talk about in a little bit, and it takes energy to move them around. And that's true for each of these. They each have a force that when it acts on a body to act in the direction of a displacement, it adds energy to it. If it acts against the direction of displacement, it takes energy out of that object. It takes energy to do that. So that's the sense in which work allows us to understand energy. We have these series of forces. If they act in our direction of displacement, it changes the energy of our system. And you might be thinking now, well, what doesn't do that? Anytime I have a force, it's going to cause motion. That's what we just learned, right? Is that forces are masses times accelerations. When does it not act in the direction of our displacement? Well, I can tell you right now, there's one that doesn't do anything like that. I can't speak for you, but I'm comfortably sitting in my chair, which means there's a normal force between my butt and the chair seat. It's pushing up, but I can roll around in this chair and it doesn't impact my total energy, right? Because the direction of the force is always pointing up, but my displacement is perpendicular to that. So it can't ever change my energy to be moving around in this chair. I'm not slowly gaining energy for rolling or losing it for having rolling around. It just is. And this is going to be really important because this is how we understand our previous system, right? Because now I want to move on to the second vocab word here, conservation. Conservation means what it kind of sounds like. It means that there's this something, this quantity that does not change, that is conserved. And so we get a hint about what might be conserved when we talked about what doesn't change in our video earlier. We saw that if we release it from a low enough height that the ramp continues, then our ball gets to the same height on one side that it started at on the other. So something doesn't change there and that thing is when we aren't moving, when our object is still, when all of its energy is in potential energy, none of its energy is in kinetic energy, then it must be at the same height. And this gives us good insight. Now we have some of the tools, I should say, to understand why that is, because our gravitational potential energy is the work done by gravity. And we know gravity as a force always points downward, which means it can only do work in the vertical direction. So we only lose gravitational energy when we decrease in height. We only gain it when we increase in height. And if we only have these two sources of energy, if we have kinetic energies and gravitational potential energy, if our kinetic energy is zero, then all of our energy of the system has to be in the gravitational potential energy. It all has to be in whatever height we are at. And so that ends up being the same at the 2 points that we are still, where our motion has stopped. Now this can be a little bit complicated to see in that demonstration where we have these normal forces, we have this rolling ball, so that it's moving in a few different ways, and we have this big loop-de-loop. We have these different paths along both sides, you notice. So let's try a slightly different system. Let's go and look at a simpler thing where we really just have one kinetic energy and one potential energy, and that's a pendulum. So what are we looking for when we say a pendulum conserves energy well? Well, we're saying that over many iterations of the same behavior, the behavior always looks the same. It's going to always return to the same starting height, and this periodic nature is just going to continue. Okay, so now we start to believe this conservation thing, that there's some quantity we're calling energy that means that we always end up at the same height in our swing. We start at a height, there's no way we can go above it. But you know what? If we really believed it, we would put something on the line. We wouldn't just swing our little IO lab cart around. We would, put something in a little bit of danger to make sure that this thing is legit. So why don't we take a look at that? All right, so now we have a really big pendulum. This one has a bowling ball attached to the end, and Mary is holding it in front of a wine glass. And when she lets go, she's going to give it just a little push, just a little extra oomph, and we're going to see what kind of damage it can cause. So now the real test. I'm going to stand in front of the bowling ball with it right up against my chin. I'm going to do my best not to give it a push, and if energy's really conserved, then it won't be able to hit me and I'll be fine.
Oh, that's a much better game face.
Okay, now we believe, right? I still have a chin, so energy's conserved. Um, and this is fantastic. So now we have our total frame in mind. We have energy defined as the capability to do work, and work is the ability to uh, enact a force across a displacement. So all we have to do is look at all of our forces that act in the direction of a displacement and count all of them up. And then once we've accounted for all of them, we know the total energy of our system and we're good to go. So now we can return and fulfill that first promise, that first definition that energy is the thing we use when kinematics doesn't work. We're going to go back to that loop-to-loop problem and we're going to solve all these pieces out. So let's take a look at it. First, we have what forces in the system? Well, we have the most obvious one is gravity. That's what's pulling our ball down, and that will do some work because the ball moves in the same direction as gravity. We have the normal force, which is pointed out of our track, but the ball always moves parallel to the track, and the normal force points perpendicular, as we talked about earlier with the chair seat. So that can't do any work. So that one's right out. And then finally we have friction, and friction is actually static for something that's rolling. So it's always just rolling along, and there's never any displacement even though the force is there, because it doesn't have any direction. It's static. It's not moving at the point of contact. So we're good. It's just gravity and kinetic energy, and I can set those two things equal to each other. At the beginning of our video, we know that we're starting from rest, so all of our energy is gravitational. And then we know at the top of the loop, we have the gravitational energy of the height of the loop plus some new kinetic energy. And this is sort of an interesting thing that we can set our 0 point for energy wherever is convenient. So the most obvious place is to measure from the table, but really the 2 points we're comparing are the most obvious places. We want all of the kinetic energy we need to continue around the loop to be equal to some amount of extra height that we're going to get by placing the ball down. So we can just find exactly that height difference from the top of the loop. So we do that, and then we mark this new height on our ramp with this nice black mark. And if we let go from here, then our ball should just nicely curl around the loop and keep on moving. Let's see it. What was that? We were so close. It was going along just fine, and then right at the top, right at that edge, it dropped off, and we heard it clang into the side and then keep on rolling. So where did our energy go? We know it's conserved. I still have a chin, but it wasn't enough to get around that circle. So right now, I'm sure many of you already have an idea about what probably happened. So what I want you to do is, again, pause the video, write down a couple of thoughts about what it might be, and then come back. Okay, so welcome back. And we're going to explore what happened. Why wasn't the energy conserved there? What went wrong? And to do that, we have to know why energy is usually conserved. We figured out that it is, but why? And under what circumstances is it not? And to do that, we're going to use two things. One is we're going to pull that very last vocab word you thought I forgot, but symmetry is something we're going to have to talk about. And we're going to rely on Emmy Noether to explain why this matters. So first of all, symmetry. Symmetry is the statement that I can make some transition in my system and it will look the same afterward. So rotational symmetry is if I were to draw a shape like a hexagon, but then I spin it 60 degrees, it looks the same, right? That's rotationally symmetric. A circle is infinitely rotationally symmetric. I can spin it any number of degrees and you can't tell the difference. And so where Emmy Noether comes in with Noether's theorem is in the early 1900s. She said that for something to be conserved, there is a corresponding symmetry of the universe, or vice versa. If there's a symmetry of your universe, then something is conserved. So that rotational symmetry, that corresponds to the conservation of angular momentum. If it's just translational symmetry, if you can move 1 meter to your left and everything looks the same, then that's conservation of translational momentum, what we learned about yesterday. Energy is an interesting one, and we want to figure out what has to be symmetric so that our energy is conserved. And to do that, we're going to take a look at a Wilberforce pendulum. Okay, so first of all, I'm going to play this video twice, so don't worry about catching all the details the first time. But this is a Wilberforce pendulum. It is a coupled pendulum where twisting the mass causes the spring to extend, and the spring extending causes the mass to twist. So inevitably, you have the energy going back and forth between these two modes. It starts entirely oscillating up and down, and then becomes entirely rotational, and then back. Wait, hold on. What was that? It was me. I played a little trick on you. The smaller video is running in reverse. I synced up the videos to begin with, and then I reversed the order of the smaller one to show, as we watch it again, that the motion still lines up. The rotation is technically in the opposite direction, but overall the energy transfer is still totally the same, because the symmetry that's respected in order for energy to be conserved is time reversal symmetry. Okay, so this time reversal symmetry thing, that's what conserves energy. That's all well and good, but why? Why is time related to energy conservation? Well, let's think a little bit more about what time reversal symmetry means. It means that if I run the video backwards like I did just now, then the system perfectly runs in reverse. So all of our forces are in the same direction, and the forces that added kinetic energy before now take it away, or vice versa. If we start with a ball on the top of a hill and it rolls on down, then if we were to run that backwards, that would be the same as giving a ball a little velocity kick at the beginning, and it rolls up the hill to the exact same spot. And that's all conservative, right? It looks the same either way. Except there's a few forces that don't work that way. It's a few forces where they always take energy away, things like friction. And so that's what we want to keep an eye for when we go back and look at our loop-de-loop to see what went wrong. All right, so we caught it red-handed. It was friction. It's not terribly surprising. It's almost always friction. But still, we found it because we knew to look for something that didn't look the same under time reversal, right? And truth be told, this isn't usually how physicists think about these things. Usually, from an intuitive sense, they try and look for where can energy go where it can't easily come back. And this is sort of just another way of phrasing time reversal symmetry. If it goes into something like deforming an object, like when we smashed that wine glass using the bowling ball, that wine glass can't easily stitch back together into its original shape. That energy of its shape has been lost. Similarly, if something gets lost to heat radiates away. It's not going to naturally come back. And so this sort of thinking about where do things naturally leave and never return leads us to our final definition of energy for today, which is energy determines spontaneous events in the universe. And for this, we actually need a secret vocab word that I left off the list earlier, which is entropy. And I left it off the list earlier because entropy is a very complicated topic. I'm going to do it a severe injustice by just touching on it in this video. But entropy, for our purposes, is going to be the number of ways an event can happen. So think of it this way. If I wanted to flip a coin 10 times, and I say, well, 5 of those times come up heads, there's a huge number of ways that could happen. It could be the first coin came up heads, or the second coin came up heads, or the third, or the fourth. All that matters is that somewhere in those 10 flips, 5 coins came up heads. The reason that's more likely than all 10 coins coming up heads is because there's only one way for those 10 coins to come up heads. So entropy, by telling us the number of configurations where the same event happens, the same final outcome happens, tells us what's more likely, where it assumes all of those states are equally likely. The one that has the most, the outcome that has the most possible states is the one that's probably going to happen. And so that's what tells us what will spontaneously happen. So how is all this related to energy? Well, there's a bunch of different ways that we write energy. We've done a few already. We wrote down kinetic and potential energies. We wrote down a total mechanical energy. At higher levels, we might have written something like a Hamiltonian or Lagrangian. These are fundamentally just other ways to write total energies. And once you get to statistical mechanics, you start defining energies for all sorts of things, for pressures, for chemical potentials, for electric charge. And one of the ones you include is entropy. There's an energy that's associated with the number of ways that something can manifest. And that is one of the only energies that's negative. So lowering your energy means increasing your entropy. Lowering the total amount of potential energy you have means increasing the disorganization of the universe. In an intuitive way, this kind of makes sense. When we put our when we put our ball up on the top of our ramp, it didn't just stay there, it wanted to fall down because its potential energy wanted to be transferred into kinetic energy. There's more accessible states if it's moving. There's all sorts of ways it could be moving. In fact, we found one because it didn't just want to move translationally, it wanted to move rotationally, even though there was some friction in the way. So lowering the lower energy state is the one that wants to happen spontaneously. And to explore this a little bit more, we're going to look at this popsicle stick bomb. All right, so what is a popsicle stick bomb? A popsicle stick bomb is where you interweave popsicle sticks such that each popsicle stick is bent as much as it can be. Each one is pushing against its neighbors, only held in place by its neighbors. And you do this in this great daisy chain so that there's a ton of energy sitting in this structure. If nothing else, this demo shows how much energy can be held just by the structure and organization of stuff. But it does show more than that because we've put an incredible amount of energy explicitly into the ordering of these things. We worked very hard to put them exactly here. And that energy is all stored. It didn't go anywhere. It's still in this structure. And because this structure is so strong compared to its components, at the lightest tap, it is going to explode. And in fact, that happened several times as we were trying to make this particular popsicle stick bomb. So the idea here is that the very nature of taking things and putting them in an order creates some energy. It takes work to do in the both literal physical as well as the metaphysical sense. And the driving force of the universe is not to be in order. It wants to have access to as many states as it can. And there's way more states available, way more organizations of popsicle sticks flung across the room than ways that you can have them be in this very straight line. And when we allow the system to realize that state, this is what happens.
Yay!
Okay, we have covered an incredible amount of ground today. We started with a lacking in our toolbox. We couldn't solve this problem using kinematics, and so we needed to invent something. And we did. We invented this new concept that turns out to be energy. We showed how it's conserved. We saw situations where it wasn't. And we learned that the reason those things weren't conserved is because they can't be reversed in time. We hopefully realized that energy is in all sorts of forms and that it's as simple as anything that conducts a force times the displacement creates energy. Or it doesn't, sorry, doesn't create energy, transfers energy. Finally, we saw that energy can be used to tell us whether a system is spontaneously going to explode or sit there calmly. If you have any more questions, go to office hours, talk to us. We're always happy to talk about it. Enjoy your lab, and I'm sure we'll talk in person soon. Bye.